Hi, everyone. My name is Karl Rittger, and as a representative of Cold World Consulting, along with ICIMOD's SERVIR-HKH Himalaya initiative, I'd like to welcome you to our training in monitoring snow water equivalent, or SWE. We're going to start today by talking about snow hydrology basics and both optical and passive microwave remote sensing of snow. When precipitation falls from the sky, it could be rain or it could be snow. While you probably already know that the temperature is the most important factor in determining what we call the phase of precipitation, there's also a relationship with humidity. The graph on the left side of this slide shows the relationship between the critical temperature, which is on the y-axis in degrees Celsius, plotted against the relative humidity, which is in percent on the x-axis. The line plotted in that graph shows at what temperature and humidity snow and rain will occur. The relationship is nearly linear and shows that for increasing humidity, the temperature needs to be colder to create snow. At the warmest extreme, on the left side at 5 degrees, if the air is relatively dry with low humidity, snow occurs. When the air is most humid, it needs to be colder, moving to the right on this graph. Much of the initial science on snow was done by the U.S. Army Corps of Engineers in 1956. The graph on the right shows measurements of air temperature plotted on the x-axis against the frequency of snow events, mixed rain events, mixed snow rain events, and rain on the y-axis. On the left side of the graph, you see at -2 degrees Celsius, all of the precipitation falls as snow. On the right side of the graph, you see that at 5 degrees Celsius, all of the precipitation falls as rain. In the center of the graph, near 1 degree Celsius, you see that about 40% of the events are either rain or snow, with just over 20% of the precipitation occurring as mixed rain and snow. For snow, there are many different types of crystal types that can be formed in the atmosphere. The picture on the left shows the type of particle, along with coding that scientists and avalanche folks use, with typical forms of each particle and their names. I won't go through the conditions that form all of these particles, but if you have access to this book, you can look further. It's probably pretty easy to find on the internet as well. Snow can melt if the temperature is above 0 degrees, but if the snow pack is below 0 degrees, metamorphism can occur, changing the crystal through vapor diffusion. For example, if there is warm air below a collection of snowflakes from the ground and cooler air above, vapor moves from the cooler to the warmer air pockets as the warmer air can hold more moisture. On the upper right side of this slide, you see a plate or dendritic particle at 0 days at the time of snowfall. You can also see the snowflake change as metamorphism occurs from 3 days to 16 days to 40 days. Underneath, you can also see pictures taken from a microscope showing a new particle and a collection of snowflakes that are highly metamorphosed. While snow occurs over large expanses, orographic precipitation occurs in the presence of mountain ranges, which lift the air. As the air is lifted, it cools and expands, dropping precipitation. As the air mass reaches the top of the mountain and it can expand to lower elevations, it warms and dries, releasing less precipitation. This process depends on the wind speed, the amount of water, the slope, and the orientation of the wind relative to the mountain. The two different sides of the mountain are called the windward and leeward sides. Warm fronts, cold fronts, and lake effects are other examples of snowfall formation that may affect the amount of snow. After snow is deposited, wind can have a significant effect on redistributing the snow. The wind speed, how rough the ground is, and the size of the snow particles all affect redistribution. The experiment shown here shows how a snow fence, which increases the roughness of the ground, modifies the distribution of blowing snow. This fence has 50% porosity, and the graph on the upper right shows 7 stages of deposition. The initial snow is deposited right next to the fence on the leeward side, but subsequently snow accumulates upward and then downwind from the fence. For this example, only 15% of the snow accumulates upwind. Snow fences are used by farmers to create drifts that help support growth as snow melts, and they're also used in windy areas to protect roads. This picture shows the reservoir created by the Tarbela Dam in Pakistan that helps control flooding and generates hydropower from the Indus River basin. Reservoirs are often built to delay winter snowmelt until the summer when more water is needed for irrigation or for generating hydropower. Snow acts in a similar way to delay stream flow to the spring or summer. The graph shows an idealized plot with sine curves representing the difference of precipitation that falls as rain versus snow. Precipitation that falls as rain may make its way to the stream channels and immediately move downstream with no delay. In contrast, snowfall is stored until temperatures warm, delaying the stream flow by months. With scientific research showing that the effects of climate change are resulting in more precipitation as rainfall and earlier snowmelt, there's a growing risk that we may lose our natural storage. Historically, and still to this day, water managers and reservoir operators want to know how much snow is in the environment to gauge the total snow volume and the management of water. In 1908, James Church developed the Mount Rose sampler, also known as the Federer sampler, to measure snow. Those are the tubes in the upper left here. The device is an open tube that is forced into the snow and then weighed. From the weight, you can determine the amount of water in the snow, also known as the snow water equivalent, or SWE, the focus of our training. You can see a team of surveyors here taking samples in California on April 1st, 2021. The Mount Rose sampler is a quick, easy way to estimate snow water equivalent, or SWE, but snow pits are another common way that generally give more precise estimates. However, they are very labor intensive, especially if the snowpack is deep. After a pit is dug, the device called a rip cutter or a Kelly cutter is used to sample the snow, shown on the upper left here. Like the Mount Rose sampler, the snow is then weighed to estimate the SWE. Let's talk about SWE for a moment. SWE is basically how much water is in the snow. This depends on two things: the depth of the snow and the density of the snow. In this equation, D is the depth. On the top of the equation, the Greek letter rho that looks like a P with the S is the density of the snow in kilograms per meter cubed. So that's a weight over a volume, kilograms over meters cubed. Rho W is the density of liquid water, also a weight over volume, kilograms over meters cubed. Dividing by the same units results in a depth for SWE. That depth is how deep the pond of water would be in a square meter if you melted all of the snow. Light snow with a low density has a smaller numerator at the top and thus a lower SWE. Heavy snow has a high density and a larger SWE. Deeper snowpacks also have more SWE. While manual measurements are useful and accurate, they are labor intensive. Another way to measure snow is with automated sensors. In the upper left, you can see a device called a snow pillow. They weigh the snow and send information wirelessly every minute or hour. In this way, you can measure both the SWE of a storm and the total SWE accumulated throughout the year. The center picture shows a typical station with snow pillows, with a snow pillow and other instruments that we'll talk about in a future lecture. In the Western US, there are hundreds of these snow pillows. The image on the upper right shows the locations of the snow pillows in the West United States. The graph on the bottom shows information from these snow pillows. It shows snow accumulating in each month on the x-axis with SWE on the y-axis. You see snow accumulating from November to April, which is fairly typical for the Northern Hemisphere. These snow pillows are in the Tuolumne River basin that supplies water for San Francisco. The graph shows the data from 2011, which was an above average year for snow in California. You can see that snow persisted until mid-July at the REL and SLI sites, the two northern high elevation sites, with snow melting out earlier than at all the other sites. On the right side, I showed two images of snow cover on July 2nd and July 18th from remote sensing. The satellite observations show a significant amount of snow persisting even on July 18th when all of the snow pillows are melted out. This example is for the highest elevation, but in general, most of the snow pillows are at moderate elevations. This means that large storms with low elevation snow are also not captured by these measurements, hence the need for remote sensing of snow. The measurements that I just showed are all labor intensive and don't cover large areas. Remote sensing, on the other hand, is well suited to provide spatially distributed, near real-time observations of global snow. Snow is highly reflective, and we can estimate the snow extent using visible and infrared wavelengths, which we'll talk about in a few slides. We can also use visible and infrared wavelengths to estimate snow albedo, or the fraction of the energy reflected by the snow, which we'll talk a little bit about today and more in one of the next lectures. Snow mass, or SWE, can be estimated from satellites using different longer wave electromagnetic radiation that is emitted from the Earth. So what is actually measured by satellites? Electromagnetic energy is measured, but from where? Passive sensors measure electromagnetic energy that is reflected or emitted from a target. In the visible and infrared spectrum, which we'll talk about shortly, sensors like the operational land imager on Landsat and the moderate resolution imaging spectrometer, MODIS, measure reflected sun energy in the daytime. In the microwave spectrum, sensors like SSMI and AMSR measure emitted passive microwave Earth energy, which can be done in the day or at night. Active sensors send pulses and measure the return, like LiDAR or radar or scatterometers, but we won't focus on those in this training. So let's talk for a moment about the signal we're measuring. On the upper right shows a series of curves derived from what's known as Planck's equation, which describe the emission from what's called a black body. At any given temperature, there is a peak in the intensity of the emitted radiation. The peak shifts towards shorter wavelengths to the left, or higher energies, on the x-axis with increasing temperature. The y-axis represents the amount of energy. The highest curve on the upper right graph is the sun, which has a temperature of 5,800 Kelvin. Since it's the hottest, it also peaks at the shortest wavelength. The Earth is 93 million miles from the sun, and the amount that reaches us is a bit lower and represented by the red line in that upper right graph. The Earth has a much lower temperature of 288 Kelvin, and thus a lower peak that is shifted to the right. For reference, a standard incandescent light bulb at 2,840 Kelvin is plotted as well. The reflected energy from the sun is what's used for optical remote sensing in the visible and infrared wavelengths. The energy emitted from the Earth, again, the blue line in the upper right graph, is what's used for passive microwave remote sensing. As energy moves through a snowpack, it's attenuated. Similarly, as energy moves from space through the atmosphere, it is also attenuated. The graph on the lower right shows the transmittance, or how much of the energy makes it through the atmosphere, as a fraction ranging from 1 to 0, along with the molecule that absorbs in those wavelengths. The place where nearly all of the energy makes it through is called atmospheric windows. Satellites measure in those atmospheric windows. Those are near 1. On the left is a graph of the energy in the visible and near infrared wavelengths reaching the top of the atmosphere, along with the amount of energy that reaches the Earth's surface after attenuation from oxygen and water, as shown on the figure on the lower right. To explain the electromagnetic spectrum a bit more, the top graph shows a squash version of Planck's curve, what we looked at in the previous slide. The electromagnetic spectrum ranges from X-rays all the way on the left at the shortest wavelengths, or the most energy, to the radio at the highest wavelengths, or the least energy, on the right side of the graph. Optical sensors like Landsat, MODIS, and AVHRR measure the sun's reflectance in the visible, near infrared, and shortwave infrared, as well as the thermal infrared. At these wavelengths, there's enough energy, as we saw on the last slide, that the spatial resolution of the satellite can be small. on the range of sub-meter to 5 kilometer. Microwave instruments that measure in the longer wavelengths require much bigger spatial footprints because the amount of energy is lower on the right side of this graph, as we know from Planck's curve. While sensors measure specific energy wavelengths, they aren't continuous throughout the spectrum, but instead measure channels or bands of data. This figure shows the electromagnetic spectrum from ultraviolet to microwave. On the top left, you can see the bands of several sensors, mostly in the visible and near infrared. The blue lines show the atmospheric windows, which line up with those bands that are measured. The red line at the bottom shows the atmospheric transmittance once again, that line up with those transmission windows. Briefly, there are a number of trade-offs when measuring the Earth's reflectance or emission. First, the spatial resolution, or how fine of a scale. Next is the spectral resolution, or what wavelengths are covered. They can be large or small, as we saw at the top of the last slide. Radiometric resolution and dynamic range tell us about how the sensor can tell small differences in brightness. That's the radiometric resolution. And the dynamic range tells us how bright or how dark it can measure. Temporal resolution concerns how often a particular place on the Earth is revisited. In addition, observations from satellites come from different orbits shown on the right. These include sun-synchronous polar orbits, low inclination non-sun-synchronous orbits, geostationary orbits, and highly elliptical orbits. Most of our work that we'll talk about in this training uses sun-synchronous orbits. This is so, as previously described, we can measure the sun's reflected radiation. Passive microwave sensors are often also on these orbits. Geostationary orbits have been coming to more use and can continuously see a single spot on the Earth. So that was quite an introduction to measuring SWE manually, as well as the background on remote sensing from both visible and passive microwave sensors. Now I'll talk a bit about snow reflectance, or how much of the sun's energy is reflected, which is on the y-axis of this graph. Also shown on the right axis is absorption, or the absorption coefficient for ice. Basically, at short wavelengths on the left side of this graph, ice does not absorb much of the sun's radiation and instead reflects it. The wavelengths from 0.4 to 0.6 are blue to red light, and snow reflects nearly all of this energy. This is why snow looks white. In the spectrum that we see, snow is reflecting all of the energy. As you move to the right of this graph, into the near infrared and shortwave infrared, ice absorbs more, and hence the reflectance of the snow drops. Fresh snow has a small grain size and is the brightest and whitest. Older snow has a larger grain size and is darker, especially as you move to longer wavelengths. This can be seen in the 4 lines plotted here with grain sizes from 0.55 millimeters to 1 millimeter. You may have seen dusty snow as well, and this is an issue in very highly grazed areas in the Western US, and also I think from the deserts in high mountain Asia. Here's a similar graph to what we were looking at before, showing the reflectance or spectral albedo on the y-axis and wavelength on the x-axis. Here, parts per million stands for, or ppmw stands for parts per million by weight. The more dust there is, ranging from 0 to 1,000 here, parts per million, the darker the snow becomes in the visible wavelengths, as well as some of those shorter near infrared wavelengths. To talk about some satellites, this table shows several satellites that are now observing the Earth, used to measure snow extent. The amount of energy the snow reflects, also called the snow albedo, and the amount of dust in that snow. We primarily use MODIS Terra, listed on top here, because of its daily observations, albeit at a somewhat coarse resolution relative to mountain topography at 500 meters. However, MODIS is reaching near the end of its lifespan, so VIIRS is a future replacement. There are now 2 VIIRS satellites in orbit, with another to be soon launched. Although it's coarser spatial resolution, analysis we've done shows that it detects snow just as well, snow extent and snow albedo. Landsat satellites have a higher spatial resolution, but a lower temporal frequency. So they're at 30 meters spatial resolution, but only pass over the same spot on the Earth every 16 days. Landsat 8 has an advantage over the older Landsat 5 and 7 in that its dynamic range is greater, so it doesn't saturate over visible wavelengths, which is an advantage for retrieving snow albedo. European instruments like Sentinel-2A and B have been launched in the last 5 years with similar spatial resolution or slightly higher to Landsat, but also a higher temporal frequency. Commercial satellite data can also be used and is a hot topic right now, but are often not as refined or as accurate as space agency satellites, and often don't include the shortwave infrared where snow is dark. We've looked at the reflectance of snow, shown on the upper right here for 4 different size grains, but now I'm showing the reflectance of vegetation on the upper left and soils on the lower left. Vegetation is dark in the shorter wavelengths, but as you move through red light to the near infrared, there's a big jump up as vegetation reflects a significant portion of the near infrared. At slightly longer wavelengths in the shortwave infrared, vegetation absorbs more of the sun's energy. Soils, again on the lower left, are dark at the shortest wavelengths, but get brighter as you move to the near infrared and shortwave infrared. On the lower right, the graph shows 1 snow, 1 vegetation, and 1 soil spectra. The vertical bars represent the wavelengths or bands that we discussed earlier, where MODIS measures the reflected solar radiation. We'll return to this graph in a future lecture. This image shows a mosaic of MODIS from a day. There's almost full spatial coverage, and the black shows those small missing areas. This daily global coverage is why we use MODIS for snow extent and snow reflectance or albedo mapping, as snow can accumulate or melt from one day to the next. To gain some local perspective, here's a region you are probably most familiar with. MODIS data comes in Landsat tiles that you can see here labeled as H22V04 on the upper left through H26V06 on the lower right. 12 tiles cover the entire study area region that spans from the Sirdarya to the Brahmaputra. The project that I worked on when I created this graph restricted funding to areas outside of China, so that's why I don't have the Chinese basins on there. This figure shows a suite of the snow surface properties that we can estimate from MODIS. We'll talk more about the algorithms used to retrieve these snow surface properties in a future lecture. On the upper left, the snow fraction, which ranges from 0 to 1, which can also be described as a percent from a 0 to 100%. The snow grain size, or the size of the snow particle, is on the right. In this figure, the grains range from 10 micrometers to 300 micrometers. Using snow grain size, we can estimate the snow albedo, which is in the left center. At the bottom is an estimate of how much additional energy from the sun as a percent is absorbed by dust or light absorbing particles on the snow. Using this, combined with the clean snow albedo, we can estimate the actual snow albedo, which is on the right center. We've done this for daily data from March of 2000 to present. For the Indus River Basin and the Western United States, we have an automated system that produces daily data. These snow surface properties are important inputs into the snow water equivalent, or SWE, reconstruction we'll talk about in a future lecture. While passive microwave sensors have a long record, which I'll show soon, Landsat provides the most continuous record of optical satellite observations. The MSS scanner measured reflectance in more bands than earlier AVHRR instruments from NOAA in the US. However, it was still limited to visible and near-infrared wavelengths. At those wavelengths, both snow and clouds are very reflective. As I showed earlier, snow reflects most of the visible solar radiation, while it absorbs nearly all of the shortwave infrared. In 1982, Landsat 4 was launched with the thematic mapper. This began the modern era of satellite remote sensing, as snow is now distinguishable from clouds. Landsat 5 was launched shortly thereafter, also with the thematic mapper, and provided data for almost 30 years. Landsat 7 was launched in 1999. While we can easily map snow from Landsat TM and ETM, Landsat 5 and 7, the more recently launched Landsat 8 has a larger dynamic range that doesn't saturate over snow and allows us to measure both the snow grain size and the impact of light absorbing impurities on snow albedo, just as I showed you with MODIS in the last few slides. Now we'll move on to focus on passive microwave satellites and mapping snow water equivalent directly. Remember from earlier, for passive microwave, we're measuring the amount of energy in the microwave that the Earth is emitting, in contrast to the visible and infrared, where we were measuring the reflected energy from the sun. The graph on the lower center shows a simple conceptual example. Basically, if there's a bare soil, we measure the expected amount of energy from Planck's curve from the Earth's temperature. Recall the blue line on the graph on the right. If there is snow over the surface, we measure a smaller signal. If the snow is deep, the signal is attenuated even more. This graph shows basically the same thing with a bit more detail. Shallow snow basically scatters the energy, and the deeper snow and the denser snow is, the more scattering occurs, attenuating the underlying passive microwave signal from the Earth. Passive microwave observations, unlike observations in the visible and infrared, can see through clouds. They have a very long history and are sensitive to moisture, including snow water equivalent. As I noted earlier in the lecture, as the wavelengths are longer than with the shortwave, pixels need to be large in order to collect enough energy. This graph isn't updated to the present, but shows the long record of passive microwave satellites starting in 1978. And passive microwave records are considered some of the Earth's longest continuous observations. So they're useful for understanding today's snow in the context of the history, as well as the impacts of climate change. In labs, we'll work with some AMSR data, which is launched in 2013, not shown here. Generally, in the microwave part of the spectrum, we use frequency instead of wavelength, typically measured in seconds to the -1, called hertz. At the frequencies we use, it's most often called gigahertz, shown on the bottom of the graph here. Like remote sensing in visible and near infrared wavelengths, water and oxygen attenuate the signal as microwaves move through the atmosphere. This table shows the frequencies of major passive microwave instruments. The frequencies highlighted are used primarily for estimating snow water equivalent, including the 18 and 30 gigahertz channels. You can see newer sensors like AMSR with new technology have a smaller footprint than old ones like SSMR or SSMI. So if you look at the spatial resolution there, it's more of a 25 by 14 kilometer instead of the older 55 by 41 kilometer, or 14 by 8 kilometers instead of the older 27 by 18 kilometers. The resolution of the raw data depends on the frequency. The most used product has been developed by NSIDC with the EASE grid projection and 25 kilometer resolution. A previous timeline I showed a few slides ago showed various satellites over time, so I won't go over these in detail, but notably the JAXA AMSR 2 instrument has been operating in the recent time period since December of 2013. The basis for most SWE products is based on the brightness temperature at different frequencies. Brightness temperature is directly related to the physical temperature of the object times a scalar called emissivity. A perfect black body has an emissivity of 1, the curves we saw earlier on the left. In the equation here, Tk is the kinetic or physical temperature, and Tb is the brightness temperature. Epsilon is the emissivity. So if we look at the graph on the right, we see the brightness temperature on the y-axis and snow water equivalent on the x-axis. There are two graphs here, one for a grain radius of 0.3 millimeters and the other for 0.5 millimeters. These algorithms assume that the grain size is the same throughout the snowpack, which might not be the case. The lower frequencies are relatively unaffected by the volume of the snow. So you see the 6.6 and 10.7 gigahertz channels on the tops of these graphs as you move from left to right for increasing SWE have about the same brightness temperatures for more SWE and less SWE. The 18 and the 21 gigahertz channels are impacted only some with increasing SWE. In contrast, the 37 gigahertz channel has a much lower brightness temperature as snow water equivalent increases and is affected greatly by deeper snow. The simplest algorithm was developed by Chang in 1987 and simply subtracts the 37 gigahertz channel, which is very sensitive to SWE, as we just saw on the last slide, from the 19 gigahertz channel that is not. That difference is multiplied by a constant that could vary, for example, by grain size. More recent work by Richard Kelly in 2009 uses a more complicated equation that also relies on the 10 gigahertz channel not available on all passive microwave instruments, primarily the older ones. All passive microwave instruments are impacted by vegetation, which emit their own signal, the depth of the snow, how snow metamorphosis has changed the snow grain size, as well as sometimes ice layers. Finally, wet snow becomes its own emitter as well, confusing the signal so that these algorithms to detect snow water equivalent are only useful for dry snow conditions. It's worth noting that there's ongoing work to estimate when a snowpack changes from wet to dry, also known as the melt onset date. One of the biggest challenges is for deep snowpacks where saturation occurs. These graphs show a validation of snow water equivalent or snow for shallow snowpack on the left and deep snowpack on the right. The x-axis is the ground-based estimate of snow water equivalent, probably from a huge sampling effort, which I showed some methods earlier in this talk. The y-axis shows the SWE from passive microwave. For shallower snow on the left graph, less than 150 millimeters, the plotted points and error bars basically follow the one-to-one line, indicating that they're a good estimate of snow volume. On the graph on the right side, showing SWE from 0 to 400 millimeters, you can see that the ground estimates are much larger than the satellite estimated SWE, and hence the graph with the blue lines and uncertainty estimates moves off to the right, away from the one-to-one line. My last few slides show a bit of the future of passive microwave remote sensing. The orbits that passive microwave sensors use create overlapping observations. Historically, to reduce noise, all observations that fall inside the 25 kilometer pixel were averaged, producing a relatively coarse output. Recently, new image reconstruction techniques that take advantage of the overlapping set of observations to create a higher resolution output are shown on the right. These figures show a comparison in the Hunza River basin, part of the Indus. The left side shows brightness temperatures for 25 kilometer pixels, the standard size. Overlaid are glacier polygons, which are much more discrete and smaller, as they're usually derived from Landsat data. The center image shows elevation at a much higher resolution. The right side shows the enhanced passive microwave resolution brightness temperatures at 3.152 kilometer resolution. While brightness temperatures have been created, there is not yet a SWE algorithm that is used on these There's not yet a SWE product at these resolutions. Ongoing work funded by the Army Corps of Engineers is supporting efforts to transfer processing to the newer JAXA AMSR satellite. So in summary, for snow hydrology, snow or rain depends on the temperature or humidity. Many types of snow crystals exist. Orographic precipitation results in windward areas getting more snow than leeward areas. Snow is redistributed by the wind, and snow is a natural reservoir. Manual snow measurement for SWE is possible, but also time consuming. And SWE, as a reminder, is the depth times the density of that snow. Automated measurement of SWE from snow pillows is possible, but there's still not complete coverage everywhere, especially in really rough regions in the Himalaya. Optical snow remote sensing, for our summary here, uses the electromagnetic spectrum in the visible, near-infrared, and shortwave infrared wavelengths. Observations in atmospheric windows with little absorption are used to measure the reflected solar radiation. Sampling is done through a set of wavelengths by bands for multispectral satellites. Snow is bright and visible and dark in near-infrared and shortwave infrared, differentiating it from vegetation and soils. Many satellites exist with different temporal frequency and spatial resolution. For passive microwave, various bands are observed at frequencies where the Earth emits. There's a long history of observations and direct measurement of SWE through the attenuated signal of the shallow versus deeper snowpack is possible. Passive microwave also sees through clouds and at night. There are still challenges in deep snowpack, forests, and areas with significant relief. Most passive microwave data is at a coarse resolution, but new data and algorithms for higher resolution will soon be available. That's all I have for now. I and others from Cold World Consulting will be available for questions in the hands-on portion of the training. Bye for now.